Good evening, Prof. Dr. Suhaimi. My name is Chua Yun Huang. Now I want to present my interim tool for project aircraft static stability and performance. First of all, this is my paper airplane with weight of ballast. So from this video, we can see that my paper plane is have a smooth gliding on the ground. After that, I got add the weight of ballast, which is 2 small paper clip and 1 big paper clip on the paper planes. So after that, I need to find my weight. Where should I set up? So I use this formula. I need to check where should I set up my weight so that my paper plane have a smooth gliding. So from here, I got put my weight must below 0.022. This is because 0.022 is my aerodynamic center for my paper plane. So I need to put in front of my aerodynamics so I can have a smooth glidings. And I get from the analytical solution, I get the weight must set up before negative 0.01117 meter. Thus, I set up my weight is 0.015 meter away from the leading edge. So after that, I need to recalculate my paper plane center of gravity. So I get this value 0.00773 meter. So from here, the top diagram is my paper plane without any weight is aerodynamic center. Just now I got said 0.022 meter, and the center of gravity is behind for aerodynamic center. After I add my weight, I get my center of gravity is in front of aerodynamic center. After that, I have do the flight test for my paper plane. Then I do 10 tests. I get the mean for the speed, leading edge. This is lift coefficient and drag coefficient. After that, I got do the standard deviation for my flight test. After I do some sample calculation, just now I got say my paper plane without any weight is this weight 0.0025 kg. After I add 2 small paper clip and 1 big paper clip, so I get my weight is 0.0055 kg, and I need to find the weight. I times 9.81 is the acceleration, gravity acceleration. After that, I use the air density is the constant, and the wing area, and the speed. I calculate this row, this column. The speed is distance over time, and the lift drag ratio I use is distance divided by height. I get this one, and the lift coefficient is lift divided by Q times A. Then I get this one. Q is dynamic pressure and A is the wing area. And this last one is CD. CD is drag coefficient. I use this formula. I get the drag coefficient is like this one. After that, I do the flight path versus time. The top one is the paper plane without any weight. I get the flight path is like this, and the flight path versus time, and the below diagram is the paper plane with the weight one. So this one have a smooth curve, and this one is like a linear graph, the top one. Yeah. After that, I have do my pitch angle versus time. From the left hand side is my paper plane without any weight, and the right hand side is the paper plane with weight. So from here we can see 2 different graph. Okay, from left first. Okay, I do the slow motion video. I can see my paper plane has spin 6 rotation before it land on the ground, and so it have a sine curve like this, though the pitching angle is positive, negative, positive, negative. From here and the right hand side, the pitching angle is negative. along the flight. Okay, so from here, from the slow motion video, I get the paper plane is gliding smoothly, landing on the ground. Yeah, so negative means my paper plane is pitched downward. Yeah. Okay, after that I got do some longitudinal performance calculations. So I get the cm alpha. Cm alpha is actually the dcm over d alpha. Yeah, cm is the pitching moment. Yeah, so I get is negative. Negative got meaning. First, negative is because of my aerodynamic center is behind of the center of gravity. So just now I got proof that my center of gravity is in front of my aerodynamic center. And if negative, also means that my pitch angle is negative. So just now I got say that this one, my pitch angle is negative along the motion. Yeah. So means that my paper plane is pitched downward when it's landing. Okay, so pitch downward means that I have smooth gliding lah. Not like previous one, I have positive, negative, positive, negative. Okay, then I got find the stick fixed neutral point. So I use this formula. Then why I put 0.05 is because stick fixed static margin is around 5% of the mean chord. Most of the aircraft it will like this, so I put 0.05 and I get my neutral point is 0.01028 meter from the nose of a paper airplane. And below this diagram we can see that CG, this is a leading edge, and CG, NP and AC. So NP is behind of CG. So from flight mechanics, what I learned it, if CG located on the XMP, the paper plane is statically stable. But in this case, our CG is not on the XMP. And next, if CG located after XMP, means that CG is right here, the static margin is negative. Means that longitudinal is unstable. From this case, my CG actually is in front of XMP. So it's the last case lah. CG is ahead of XMP, so my paper plane is positive static stability. So I get positive static margin. And I got do some calculation of my trim speed of my paper planes. So I get this value. After that, I get the drag polar curve. So drag polar curve, I from this drag polar equation is CD equal to CD naught plus KCL square. So from here, so means that my x-axis is CL square and my y-axis is CD naught. Yeah. So from here, I plot it CD versus CL square. So I get my K value is 0.1966 and CD naught is 0.117. So this is all my interim part 2. Thank you, doctor. Have a nice day.